I was really panicked yesterday. I went to upload the video and it said like no video to data to process, and I was like, no, the best lesson ever, no. You may not have thought of it as the best lesson ever, but it was a Monday morning. It's the series unit. Life is rough. It's going to be fine, and it's just gonna get better, just like all the other things that we've ever done. This is the unit that's going to rock your socks. This is the unit that is going to take more. It's going to take more than what you have done before. Not more than you're capable of, more than you've done before. Okay? So if you feel good about the homework that you did last night and you're ready to put that in the middle of the table, feel free to do so. If you're kind of like, I'm not really ready to turn this in, I am available during lunch. Stop by during lunch with your questions. I have got to leave right at 1 o'clock. Right at 1 o'clock, I got to go. Celeste, are you okay?
Yeah.
Why are you Mad Dog and Carmen? What did she do to you?
Because you have no eyelash. And Myra all have A's during lunch.
Oh, bummer. Well, good luck. So, all right. So, couple of thingies. Tonight's homework is assignment 108. You're going to want to write this down because some of you are going to go home and think I said do all of it. Don't do all of it. I do want you to do problem 1.
Wait, didn't we just do that?
Is it 108?
Yeah.
You mean 110?
110.
Wait.
110 could.
Hold on, I make the decisions here.
There's no 20
We
on
have
it. There's no 20 on it. You don't have
Hey, no homework, guys.
It must be 110. 110. How awkward. 110. So assignment 110 is to do problems 1, 3, 4, 5, 6, 7, 9, 13, 15, 16, 20. I won't repeat it. It's up there. This is due Thursday. I want that to come through loud and clear. This is due Thursday. The smart teenager is the teenager that's going to go home, do as much of this they can tonight, and come in tomorrow during lunch if you have some questions or have some issues. It's due Thursday. You should be able to do all of it tonight. What is due tomorrow are test corrections for the polar, vectors, parametrics. For a lot of you, you did really well. You have only a couple of corrections to make. If you need some support, see me during lunch. Okay. Lewis, we already talked. And cookies. The only cookies I have available now are peanut butter patties and Thin Mints. Everything else is gone. It's off the table. All right. So let's get started with just a quick review. Sequences, series. What's the difference? What's the difference between a sequence and a series? Have a quick conversation with somebody near you. What's the difference between a sequence and a series? Stop eating. Start talking. Sequence and series. What's the difference? Okay, so a sequence is just a list of numbers. A series is a sum of these infinite number of numbers. We are focusing on series, all of the problems. So Stephen, make sure I want to get everybody over here. So when it comes to a sequence, we're just saying it's a list. A sub 1, A sub 2, A sub 3, so on and so on. It might end, it might not end. If it ends, it's a finite sequence. If it doesn't end, it's an infinite sequence. Now, up until this point, I've always listed the first term as A sub 1. That's not necessarily the case. Sometimes there's a 0th term. You can start at 0, you can start at 1. The rules of the road are you can start anywhere you want. Generally, we constrain ourselves to natural numbers, 0, 1, 2, 3. There's no like term 2.5. Okay, a series is just a sum. It's an infinite sum of these terms. Okay, if I told you you have an arithmetic sequence, what does that mean? Arithmetic sequence means that there's a common difference. If I tell you there's a geometric sequence, there's a common ratio. If I tell you that the series is geometric, so a geometric series is going to have the form, I'm doing a sum, maybe from 1 to infinity, of a times r to the n, or a times r to the n minus 1. If you want to write it that way, that's fine. The a is your first term, and the fancy word, the letter r is your common ratio. What I need you to know is that if you have a geometric series, that geometric series will converge or it'll diverge. How do we test for convergence if you have a geometric series? Just Stephen, Celeste, Myra. The test, it's a really quick test. There's one thing that you test. Myra, what do you test?
The test has that geometric, and then the common ratio is less than 1.
If the common ratio is less than 1, converges? I don't 100% agree. It is so close. I am wicked picky here. It must be the absolute value of the common ratio is less than 1. You will diverge in all other cases. Any other value of the radius, if absolute value of the radius is greater than or equal to 1, you diverge. Now the nice thing is, in the world of a geometric series, where the absolute value of the common ratio is less than 1, we know we converge. Even better, we get to address the second question that we sometimes care about, which is, what does it converge to? What is the sum equal to? And there's a formula, and that formula is?
1
No,
over
a over 1 minus 1.
A, your first term, not 1, but the first term. And then?
1 minus.
1 minus r. We proved it yesterday-ish. You may remember that. You may not remember that. You just need to know that the sum for a geometric series, it is one of the only series we can actually get the exact value for. First term divided by 1 minus r. Everybody okay? That was geometric series. The other thing we talked about yesterday?
No, nth term test.
The nth term test. The nth term test for divergence. It is only to be used for divergence. So the nth term test for divergence basically just says something like, if I have this infinite sum, those are my a sub n's. Eileen, do you remember what the nth term test for divergence says?
If the limit is not equal 0, then it diverges.
Perfect. If the limit as n approaches infinity of the term, not the series, the term, if that is not equal to 0, then the conclusion, then the series, the sum from 1 to n of a sub n, diverges. You can only determine divergence from the nth term test. You cannot determine convergence, and it's the series that diverges, not the sequence that diverges. And the last thing we talked about yesterday was?
Telescoping.
Telescoping. A telescoping series, we just expect terms to be canceling out. A couple of the terms survive. That's the sum. That's everything we've done so far. Are all the friends okay? You guys ready to have your world rocked? Yes, excellent. Good answer. All right, so new one for you today, the integral test. This one is heavy. It is heavy. It is just going to be heavy for a little while. It's going to be okay. What we're actually going to do is we're going to use the integral test, and then we're going to prove the integral test. You might want to take out your calculator. You definitely want to take out your smarticle particles. Hopefully you brought them to school today. You're going to need them. This is going to be probably one of the first tests of many where you're going to be like, oh my God, somebody way smart came up with this. Yes, somebody way smart came up with it. No, it's not me. Here's what the integral test says. If f is a function If f is a function, which is three things, you have to have all three. Positive, continuous, and decreasing. If the function satisfies all three of these conditions, then if your series goes from 1 to infinity or 0 to infinity, and the definite integral are going to do the same thing. I need to say that again. I need to start it differently. I've got a series, right? Just the sum of an infinite number of terms. What you start with is this. You have a function that will actually generate the same terms for you as your series does. Meaning if your series is like 3, 9, 12, 18, whatever, if you can find a function that generates those terms, if the function is positive, continuous, and decreasing, then if the integral converges, the series converges. If the integral diverges, the series diverges. So one more time. You're going to start with the series. You're going to find a function that actually generates the terms of the series. And if that function is positive, continuous, decreasing, whatever the integral does, the series does. Converges, converges. Diverges, diverges. Kind of okay? All right. Furthermore, if what I wanted to do is look at a partial sum, S sub n is your nth partial sum, the partial sum is going to be different from the true sum if you added everything up. The S is the true sum. If I look at S minus S sub n, this is like the difference, so I'm going to call this the error. Some people call it the remainder. The remainder is going to be less than or equal to the integral from n to infinity of f of x dx. This is the integral test. That probably felt like gobbledygook. But the key, the whole thing that we're focusing on in this whole unit on series is, does the given series converge or diverge? And if it converges, can we figure out what it converges to? What you're doing, if you do an nth partial sum, you okay there?
Yeah, I'm good.
Okay. By looking at the nth partial sum, what you're saying is, let me add up not all the terms, but the first bunch of terms. Are we okay with that, this idea?
Mm-hmm.
If I add up the first bunch of terms, am I going to get the true sum?
No.
What you're going to get is a
Partial.
partial sum. What you're going to get is an approximation. You're going to get a best guess as to what the true sum is. And so the difference between the true sum and your partial sum is the error, or it's the remainder. The remainder, how much you're off by, will be bounded, trapped, less than or equal to this definite integral. This is the integral test. Pretty okay? Let's just use the integral test, and then we'll loop back around. All right, so let's look at this first model problem. So this is what it's going to look like. You're going to be given a series. The integral, hello. And I want to know if this series converges or diverges. So I'm looking for the sum from 1 to infinity of n over n squared plus 1. The question is, does it converge or diverge? Well, let's start with our basics. Is this geometric? No, if it was geometric, it would have that form of like a times a number raised to the nth power. It would have an exponential form. It's not geometric. Telescoping, I would expect to see like two fractions and some subtraction happening. Not happening there either. So let's try the integral test. In order to do the integral test starts off first by identifying a function. And the function that I'm going to pick, if this is my series, the function is going to be f of x equals x over x squared plus 1. Basically all you're doing, if these guys over here are your a sub n's, I'm going to make a function that has that exact same form. And what I'm interested in now are three things. Is the function continuous? Is the function positive? And is the function decreasing? Now to help you guys with this, just to make sure we're all on the same page, I included a graph of the function. This is cheating. This is absolutely cheating, but I at least want to get us all on the same page here. If that's the graph of the function, does it satisfy all three criteria? All three? Not always decreasing. You haven't satisfied all three criteria, Lewis. There you go. So if I start over here at n equals 1, now ask the question again. Does this function satisfy the criteria? Continuous? For sure. Positive? Of course, always above the x-axis. Decreasing? I can see it. That isn't going to be good enough. What we need to do is we need to use our calculus skills to actually show each of these three things. Okay, so let's start with continuous. Is the function continuous? Imagine you couldn't see it and you had to make a determination about continuous or not. What would we do? For continuity. No. Continuity. Not differentiability. Lewis, what would you do for continuity? Okay. It's really easy. You guys are totally overthinking that. Look at that function. X over x squared plus 1. There's only a couple of reasons why a function would fail to be continuous. Like 0 in the denominator, which causes asymptotes and poles. Can this function ever be discontinuous? Right? I'd say like x squared plus 1 is never equal to 0, therefore f is continuous everywhere. Now, really, we don't need continuous everywhere. What we need is continuous for x greater than or equal to 1, because that's what I need my function to be. We've got continuous. Okay, positive. I need to be convinced that this function is positive for x greater than or equal to 1. If I pick x values greater than or equal to 1 and I plug them into this function, guess what? They're all positive. X is always greater than or equal to 1, therefore positive. X squared plus 1, yeah, always going to be positive. So you might even just be like, yeah, check. The last one is the tricky one. Decreasing. The way that you're going to check decreasing, if f is decreasing for x greater than or equal to 1, then what my calculus brain tells me is that f prime of x has to be positive for x greater than or equal to 1. You're going to have to check all three conditions. So let's find the derivative. Let's find the derivative the nice way here. Derivative of x over x squared plus 1. Quotient rule. Low x squared plus 1 d high 1 minus high d low over low low. The question that you have to ask yourself is, will this always be negative? You might want to clean it up a little bit. X squared plus 1 times 1 is x squared plus 1 minus 2x squared. Yep.
Shouldn't f prime of x always be less than 0?
Thank you so much. F prime of x is less than 0. Thank you. Thank you for that. Negative x squared plus 1, x squared plus 1 squared. That's the derivative. Is the derivative always going to be negative?
Yes.
Right? Think about this. You're picking numbers like 2, 3, 4, 5. You're taking that number, you're squaring it, you're making it negative. You're adding 1, still negative. Denominator, always positive. Less than 0. Here's the good news. You have picked a function that did 3 things. It's positive, continuous, decreasing. Attack those in whatever order you want to. You know what this means?
You can use
It means I can use the integral test. That's all that it means. Therefore, we can use the integral test. It doesn't actually mean converges or diverges. It just means it is legal for me to use this test. And what the test says, Stephen, I'm going to be over here. So what the integral test says is, let's look at the integral from 1 to infinity of x over x squared plus 1 dx. Now, just because there might be some like really good calculus teachers out there watching the video right now, this is a different kind of integral than we have ever looked at before. This integral is different in what is an obvious way. We're integrating to infinity. We've never actually done this before. This is what's called an improper integral. We are going to talk about improper integrals, but not until later in the course. Improper integrals are supposed to be handled differently than we're going to do it right now, but it's okay. It's okay, stay with me, it's legal. All right, what I need to do is I need to integrate this function. Integral of x over x squared plus 1. Well, what are my options here? Integral of x over x squared plus 1. We're hitting all the skills now. How would I ever integrate something that looks that messy? How about substitution? If I'm going to do substitution, what's the u? X squared plus 1 is the u. Then we find the derivative. du dx is 2x, which means du is 2x dx. Maybe you want to multiply both sides by a half to get 1/2 du equals x times dx. Now you've got to be really careful, because when we do our substitution, you don't just rewrite the integral and say, oh, 1/2 du over u. You also rewrite the limits of integration if we're going to do this correctly. If x is 1, what's the u value? If x is 1, we come over here, 1 squared plus 1 is 2. If x is infinity, u is infinity squared plus 1. Guess what? Infinity. The reason you did substitution is that hopefully you get something that is easier to work with now. For example, I can take that 1/2 out, it's a constant, and I'm integrating from 2 to infinity 1 over u du. The integral of 1 over u is the natural log of the absolute value of u from 2 to infinity. We're going to plug in 1/2 the natural log of infinity minus 1/2 the natural log of 2. And we need to make a decision here. What's that equal to? Is that converging or is it diverging? The natural log of infinity. It's going to be infinity, right? Think about your graph of the natural log. The graph of the natural log is increasing. This guy here is approaching infinity. Minus 1/2 the natural log of 2. Natural log of 2 is 0.693. Who actually cares? You have infinity, and someone has taken away half of 0.693 from you. What do you have? Infinity. You have infinity. Therefore, your conclusion, what happens with your integral, the integral from 1 to infinity of x over x squared plus 1 dx diverges. Don't stop there. Don't stop there, because you're actually not really interested in the integral. The question wasn't about the integral. We're in a unit on series. The question is about the series. The integral test, the beauty of the integral test is it actually gives us something we can do over here, right? Something within our skill set to be like, oh, I can integrate, okay, maybe. I can get an integral and I can look at that answer and say the integral diverges, so guess what? Therefore, the series, and you always have to conclude with the series, n over n squared plus 1 diverges. And to be really good, diverges by the integral test. This, my friends, is the opening problem for the integral test. This is how the integral test works. We haven't proved it. I do plan on filming the proof part later, and I'll just post that so you guys can see it, but I wanted to make sure we were getting some practice. You're not really going to be assessed on the proof, but I want you to be able to see the proof. What questions are out there? Celeste.
So if we're not supposed, okay, so for right now, it's okay to handle improper integrals like that.
It is okay to handle improper integrals this way right now. I've looked at the College Board scoring rubrics, and even when you need to do the integral test on the free response part of the test, and you get to something that's an improper integral, I think I'm having a conversation mostly with calculus teachers right now, it is okay to do this and not do it the right way to handle improper integrals. There's a right way and there's a kind of not 100% right way. We're in the not 100% right way place. But it's okay.
So we get all the points.
What?
We'll get all the points.
I would never show you anything that would get you anything less than all the points. Because I care about you. You, Lewis. Just you. Alright.
Well.
The other 9 losers, you okay? Alright. Alright, so let's see what you can do. I am confident some of you are ready to just spring into action on your own. If you want to go